Hi everybody, so it's time for me to do the next video, and today I would like to speak about how to use S parameters or how to extract RLC values and impedance values from S parameters, because I know, probably you know S parameters are very popular in high frequency engineering and antenna engineers or filter engineers for high frequency applications. They use them every day, but somehow I have the feeling that they are not that popular. So when I meet power electronics engineers, they're always thinking RLC values, and they say, S parameters, that's not really our way to think. However, there is a very convenient way how to use S parameters and convert them to RLC values, convert them to values that maybe can be much better grasped, can be understood much better. And for this, I created a simple example in the simulation, but of course be aware that this might be also a set of S parameters you obtain from measurement. So the S parameters are of course not exclusively for simulation, but I do exclusively simulation. So that's why I also use such a model. So we have a simple model. It's just basically a microstrip of a ground with some certain dimensions, 10 centimeters length, half millimeter of thickness, 300 microns of width. That doesn't matter that much. It's just as an example. So let me hide just these dimensions to explain more. And then of course we drive the microstrip line against the reference, or you want to call it ground. It might be the same like when you do a measurement, putting a SMA connector, inner of the SMA here, outer of the SMA here. And when you do the measurement, or when I do the simulation, what we get is of course the S parameters that tell me, okay, of course I have a great transmission, it's a well-defined system, there are not many obstacles, and you don't expect any impedance changes, so we have a great transmission, but that's basically all that we see from the S parameters. Now imagine you would like to, for example, understand what is the resistance of this setup. First thing, obviously, is we cannot extract from our S parameter values just the resistance of the signal trace. What we can always do is the resistance of the loop or the inductance of the loop, but just for the trace itself, that's not possible, because in the S parameters you have, the S parameters are always defined with like inner and outer, right? So you reference your signal trace to the plane, and you do the same on the other side. So what we can do is, of course, we can think like this: if we put a signal here and we short this side, then we get the loop resistance or the loop inductance. If we put a signal here and open this side, we can calculate the capacitance between the trace and the ground. And I want to show you how to do this, because sometimes it's not that obvious, because the inductance itself is of course the Z parameters, but if we have a two-port setup, how will the Z parameters look? Like this. That's the Z parameters. And people tend to say, hey, there's something wrong here, did something wrong go here, why do I see such a high value? But that cannot be the impedance of the loop. And it is not, because these are the two ports Z parameters. And if you look up, for example, in Wikipedia, you see for equivalent reciprocal circuit, the Z parameters are defined like this. I don't want to go in explaining the Z parameters, but what we could do, of course, we could use this equation to calculate the loop impedance just by setting the load. Well, like I said, if we want to have the loop impedance, we set the second side, which is in this case the load, we set the second side to 0, we short. So we set the impedance on the second port to 0, and we use this formula, right? We can do this. So I can go into the post-processing steps and type in these equations. And if I do this, so you see the D, and in the denominator, the termination impedance or the load impedance is set to 0. And if I do this, I get the loop impedance. So this is the loop impedance, which shows me, let's plot the double logarithmic, of course. Up to here, it behaves purely resistive. Then it's becoming more inductance. The impedance is governed by the inductance. It's fine, but it's such an effort to type in these equations. Of course, there's a much smarter way, and this is done doing some modifications of the circuit. So simply inside this block is again the S parameters. So the 3D solver passes on the S parameters to my circuit. And what I do is I just simply now short the other side. So what does the setup mean? This port is a source, or now for the S parameter calculation, it's a 50 ohm port at the one side and a short on the other side. And if I calculate the S parameters, obviously, I don't see something like a transmission because all the signal is coming back. It's flowing in the loop. So the S parameters now are a little bit meaningless. But now I can look at the Z parameters like I did before, and I obtain exactly the same thing, but without typing the formula. I just use the circuit to do the math for me. And I'm getting the same response. You can see that's the response I calculated with my formula. But this is now the Z11 calculated on the circuit just by shorting the other side. And if I have the loop now, I can easily calculate the inductance and the resistance of the loop. You can now look up formulas. You have to divide over 1 over omega or whatever. Don't mind. Take a post-processing template and just calculate resistance for Z11. And it's important that I made this reduction from the two-port network to one-port network by shorting the second side. And we can calculate easily the resistance. So we see for our particular setup, a DC resistance is something like 165 milliohm. And I'm getting the inductance, which is 48 nano Henry in this case for this length. So that's fine. Obviously, you see that at higher frequencies, L becoming negative and all the things. That's simply because you have resonances. That's what we have seen in the Z parameters. Once your structure is behaving resonant, the meaning of L11 is the meaning of the inductance is very, very limited. And I tend not to use this. Your circuit can no longer be described by one inductance value. And calculating the inductance is still possible by doing the math, but the meaning of it is very limited simply because you cannot describe the properties of your structure just by one inductance. So we have nice results for L11, we have nice results for R, so inductance and resistance is fine. But there's a problem with the capacitance. If you look what happens here with the capacitance, it's becoming negative at low frequencies. And the problem is the shorting we did, because for the capacitance, we want to have the capacitance between the trace and between the ground. So if we short the one side, basically we have just one loop, one conductor, and that's not how you obtain capacitance. But there is an easy way to do so. You just need to change the schematic. So let me use a so-called clone block. So that's basically a clone of this one. And what I do now is I put a second port. I put a second port here, and I calculate the second impedance for an open circuit, right? And for the open circuit, if we now go into the calculation of the capacitance, and instead of using 1,1, obviously I use 2,2, which is the impedance of the open circuit. And if I calculate this, we can see that we now get a meaningful capacitance of 9.3 picofarads. That's what you would expect from this very thin trace. So I think that's where people often struggle when they have these touchstone files and they try to manipulate them and calculate impedances, and then they see values which become negative and they are confused what's happening. So it's pretty simple. If you have a two-port, for calculating resistance and inductance, you have to short the second port. For calculating the capacitance, you have to open the second port. And then it's very, very straightforward to get the right values and get the RLC description, which works well at the low frequencies. So pretty straightforward, I think pretty simple, but people can overlook this, and I hope it was helpful for you. So this time short for today. Don't forget to hit the like button and subscribe, and stay tuned for the next videos. Bye bye.